to the Chapter 8 Part 1 video. This covers 8.1 and 8.2. In this chapter, we're going to be talking about radicals, specifically the Pythagorean theorem and how they relate to triangles. So finding sides of triangles and how we'll use radicals for that. So our objective for 8.1 is to use the Pythagorean theorem and its converse. Hopefully you're a little bit familiar with the Pythagorean theorem, but the converse might be new to you. So in order to do this, we first have to be able to recognize perfect squares. So we started talking about this a little bit yesterday, but perfect squares are when we can take a number and have two identical factors. And so we can say that the square root of 0 is 0, and we can say that the square root of 1 is 1, but we can't have a perfect square root of 2 because 2 doesn't have two identical factors. And so when we're making our list, really underneath the square roots, we only want very specific numbers. So if we can think about it, what is the square root that will give us 2? Well, 2 times 2 is 4, so the square root of 4 is 2. Now, the reason we're not putting a plus or minus here, remember I said whenever you take the square root, you have to put the plus or minus. Well, if I'm given the square root, then I know that it's positive. It would have a plus or minus in front of it. If I have something that I'm creating the square root, there was no square root, now there's a square root, that's when we have to put the plus or minus. We'll talk about that more throughout our examples. So we have the square root of 4. The next one will give us 3 as the answer, and that is the square root of 9. To get 4 as the answer, we get the square root of 16. And so we're looking at all of these numbers that are inside of the radicals are what we call perfect squares. 0, 1, 4, 9, 16. Those are perfect squares. So the next perfect square should give us 5, and that's 25. To get 6, we take the square root of 36. For 7 is the square root of 49. 8 is the square root of 64. 9 is the square root of 81. 10 is the square root of 100. 11 is the square root of 121. 12 is the square root of 144. 13 is the square root of 169. 14 is the square root of 196. And then 15, this will be our last one, is the square root of 225. So I said to go between 0 and 200, but we didn't really know that we had gotten up to 200 until we found one above it. Okay, so these are ones that it would be very useful to recognize. You don't have to memorize them. You do have your calculator. However, the easier it is to recognize them, the easier it will be to do your computations. Okay. As far as using these in algebraic computations, we've already taken a look at simplifying radicals. So as a reminder, in order to simplify a radical, we want to look for its factor tree because we can recognize the square root of 8 is not one of our perfect squares. And so we need to factor this. And it works for perfect squares as well. 8 is 4 times 2. I don't have any common factors, but 4 actually reduces to 2 times 2. And so I have this pair of 2's and this 2 that doesn't have a pair. And so the pair of 2's is reduced to 2, and the 2 that didn't have a pair is left under the radical. 2 times the square root of 2. We'll do the same thing for 108, which is 9 times 12. 9 can continue to factor into 3 times 3. 12 is 3 times 4. So there's a pair of 3's and 1 3 left over, and the 4 factors into 2 times 2. And so what we have now is that we have a factor of 3, a factor of 2, and a 3 left under the radical. And really these are all multiplied, so this becomes 6 times the square root of 3. Now, the reason we don't do 6 times 3 now is because the 6 is outside of the radical and the 3 is inside of the radical. And that was the whole point of doing this factor tree, is to find out which of these can reduce from their perfect square form. So for part C, now we have a 4 outside of the radical. It's going to stay outside of the radical. And we'll factor the 125. So I'll factor it down here. 125 is 25 times 5. 5 is prime, so I'll continue to factor 25, which is 5 times 5. 5 times 5 with 1 5 left over. So times 5 times the square root of 5. 4 times 5 is 20 times the square root of 5. But what if I'm not multiplying or simplifying these radicals? What if I'm adding and subtracting? Well, to add and subtract, we're looking for like radicals or like terms. So when in doubt, pretend that it's an x. So if this is x and this is x, we can think about this as 7x minus 2x, which we know we can subtract to get 5x. Well, radicals work the same way. Because the square root of 3 is the same as the square root of 3, we can say 7 times the square root of 3 minus 2 times the square root of 3, just like we did here, is 5 times the square root of 3. If the radicals don't match, if the radicals are not identical, so let's say this is square root of 5 and square root of 3, we can't combine them. If there's no square root with square roots, we can't combine them. So 12 stays by itself, nothing to combine it with. But 3 and 7 both have this square root of 5. Those are like. 3 minus 7 is negative 4 times the square root of 5. And then lastly here, we don't have like radicals. They're not like terms. The 2 and 18 don't match. However, 18 can be factored into 9 times 2. 9 is 3 times 3. So we can actually rewrite this. 10 times the square root of 2 minus 3 times the square root of 2. Now they are like terms. They have the same radicals. So we can say 10 minus 3 is 7 times the square root of 2. So let's do a little practice. I'm going to give you a second to do these examples. I know that I kind of cut out the number 4, 5, 6, but just do these 6 examples here and then we'll run through them together. All right, for number 1, starting by factoring, I say that's an even number. I'll factor out a 2 times 21. 21 is 3 times 7. None of those factors are common. I don't have any duplicates of any of them. And so the answer is just the square root of 42. That one can't be reduced. For number 2, this is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So there's my pair of 2's. 2 doesn't have a pair. 3 doesn't have a pair. That gives us 2 times the square root. What's stuck inside is a 2 and a 3, giving us 2 times the square root of 6. 500 is 5 times 100. 100 is 10 times 10. Even though those aren't prime, they already match, so I can group them together. The 5 does not have a pair, so it's stuck inside the radical. This gives us 10 times the square root of 5. For the next one, we have here, they both have a square root of 2. This is 18. This has an invisible 1, just like if it was an 18x minus x. 18x minus x would give us 17x. So this gives us 17 times the square root of 2. Here we have the same radical. 6 plus 8 is 14 times the square root of 3. And here again, same radical, 8 plus 12 is 20 times the square root of 5. Let's take a look at the next page. So the Pythagorean theorem, hopefully you've heard of this. Pythagorean theorem is one of those theorems that will come up over and over and over again. And it's a squared plus b squared equals c squared, where c is the hypotenuse. So c is always the biggest side. Right? Always across from the right angle. So this could be A, B, and C. A and B are interchangeable. So if I had switched that, if I had done B, A, C, still the same equation. Because if I switch those two, because addition is commutative, it will stay the same. Some important numbers to be able to recognize, and the most commonly used are these first two. They're called Pythagorean triples. And these triples make perfect Pythagorean theorem equations without having any radicals left over. So normally, if I were to plug in numbers for A, B, and C, one of them would have to end up being a radical, except in the cases of these numbers and their multiples. So 3, 4, 5, that says 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. 8 squared plus 15 squared equals 17 squared. 7 squared plus 24 squared equals 25 squared. And you can verify those, but I promise you they work. What it means by and their multiples means that I can take these numbers, and as long as I multiply them all by the same number, it will still work. So let's say I decide to come in and multiply these all by 3. Then this would become 9, 12, 15, and it will still work. And I can show that to you here. If I say 9 squared plus 12 squared, it should equal 15 squared. And they do equal the same, they do equal the same thing. Okay, I could have multiplied by any number to get that multiple of a Pythagorean triple. So let's see how this works. In order to apply the Pythagorean identity, the first step is to identify the hypotenuse. There's my right angle. Across from that is my hypotenuse. That's the one that's going to go by itself. So we have 6 squared plus x squared equals 10 squared. Solving for x, I'm going to subtract 6 squared from both sides. X squared equals 10 squared is 100, 6 squared is 36. 100 minus 36 is 64. And here's where we use the square root property. Notice there is no radical. So when I create the radical, I need to put the plus or minus. There was no radical before, there was no square root sign before, now there is. And so we can say the square root of x squared is x equals plus or minus the square root of 84 is 8. However, notice x is a length, so we will choose the positive one. For this chapter, almost always we'll only need the positive one, but you still have to write in that step because it is mathematically correct to have the plus and minus. And so x equals 8. Okay, go ahead and try these next 4, and then I'll go over them with you. So for number 2, here we're solving for x. First step, find the hypotenuse. So 5 times the square root of 2 squared plus x squared equals 8 squared. Simplifying, I'm going to subtract 5 times the square root of 2 squared minus 5 square root of 2 squared. So that's x squared equals 8 squared is 64 minus, how do I compute 5 times the square root of 2 squared? Well, when I square something, I'm multiplying it by itself. So 5 times 5 is 25. Square root of 2 times the square root of 2 is 2. How come I'm not foiling? Because there's no addition or subtraction. So think about this as 5 times 3 times 2. Well, I can choose to do 5 times 2, which is 10, times 3, which is 30, right? So I can choose what order to multiply them in. So when we're multiplying numbers that have radicals in them, multiply the part outside of the radical, and then multiply the part inside of the radical, and then multiply those together. So this is minus 50. Then we have x squared equals 64 minus 50 is 14. Take the square root of both sides, meaning I need the plus or minus. Then x equals plus or minus the square root of 14. Well, 14 is 2 times 7, no copies, so it can't be simplified. X is a distance, so I choose just the positive. X equals the square root of 14. Notice I had to check to make sure that this was reduced before I can put it as the answer. On the next one, for number 3, find the length of HP. First, we label our hypotenuse. Hypotenuse here, we don't know it, so let's find C. 9 squared plus 12 squared equals C squared. Well, if you'll recognize, we actually just saw these numbers a moment ago with the Pythagorean triples, but let's do it computationally. So 9 squared is 81, 12 squared is 144 equals C squared. 81 plus 144 is 225. Take the square root of both sides. Then plus or minus 15 equals C. C is a distance, we take the positive. C equals 15. On number 4, identify the hypotenuse, that's C. We don't know this side. However, we do have these congruence markings, making this an isosceles triangle, and therefore this side is 2 times the square root of 6. So we have 2 times the square root of 6 squared plus 2 times the square root of 6 squared equals x squared. Well, remember when we square a number, we multiply it by itself. 2 times the square root of 6 times 2 square root of 6. That gives us 4 times 6, which is 24. So that's 24 plus 24 equals x squared. 48 equals x squared, square root on both sides. X equals plus or minus the square root of 48, which is 4 times 12, 4 times 3, gives us plus or minus 4 root 3. X is a distance, so we take the positive one. X equals 4 times the square root of 3. And our last one for this page, find the values and variables. You actually have a couple of options on what to do here. Because we know that vertical angles are congruent, we can use the properties of similar triangles from yesterday and the day before, or we can use Pythagorean theorem. So I'll show you both ways. Method 1, Pythagorean theorem says, here's my hypotenuse, 4 squared plus x squared equals 5 squared minus 4 squared. X squared equals 25 minus 16, which is 9. Square root x equals plus or minus the square root of 9, which is plus or minus 3. It's a distance. X equals 3. We also need y, which is also the hypotenuse. So we say 8 squared plus 6 squared equals y squared. 64 plus 36 equals y squared. 64 plus 36 is 100. Y equals plus or minus the square root of 100, which is plus or minus 10. We need the positive one, so y equals 10. Second method is with similar triangles. I'll use my colors for this. The side between the two known angles, the hypotenuse of each triangle, and the other leg. Setting up my proportions. If I want to solve for x, I'll do blue over, which one do I know all the numbers of is orange, blue and orange. So that'll be x over 4 equals 6 over 8 times 4 on both sides. X equals, this reduces, so that would be 3. To solve for y, I want to use pink. Over the known is orange. So that would be 5 over 4 equals pink over orange. Multiply both sides by 8. That reduces to 2. Y equals 10. Both completely viable options because these are right triangles that we can prove are similar by the angle-angle similarity. I should say by angle-angle similarity. That's why we could use that. Let's take a look at our next page. A couple of application problems. We'll do these together. So for this example, we have a 20-foot ladder leaning against the side of a house, similar to a question that you had on your homework. Here's my house. Here's the ladder. Here's the ground. So we know the ladder is 20 feet. The distance from the foot of the ladder, that's the bottom of the ladder, to the bottom of the house, that's here, is 12 feet. How high up the wall is the ladder? So how high does the ladder lean against the wall? We'll call that x. X is height of ladder touching wall. So here, because houses are built straight up, this is a right angle. This will be my hypotenuse. X squared plus 12 squared equals 20 squared minus 12 squared. X squared equals 400 minus 144. 400 minus 144 is 256. X equals plus or minus the square root of 256, which I recognize, I believe, is the square root of 16, plus or minus 16. It's a distance, so it has to be positive. X equals 16. For our second one here, it's a little tricky because you have to read the question carefully. How much shorter is it to get from your house to McDonald's if you don't stop at Maria? So the question is, if I walk from my house to McDonald's, it's going to be a certain length. If I walk that same route, but I stop at Maria's house on the way, It's going to be a certain length. And I want to know how much shorter is it to walk straight to McDonald's without stopping at Maria's. And that means I need to know how far is it on this hypotenuse length to McDonald's. This is our hypotenuse. So we say 16 squared plus 30 squared equals x squared. 16 squared is 256. 30 squared is 900. 9, so that's 1156 equals x squared. To find this, x equals plus or minus the square root of 1,156. I don't recognize that as a perfect square, so I'm going to, remember we said the square root symbol, if I find the 7 and I go up and over, there it is, I have to do second square root, and it'll put in the square root symbol, 1,156. Enter is 34. So it was a perfect square, plus or minus 34. It's a distance, so it has to be positive. 34 miles to McDonald's. But the question wasn't how long it is to get to McDonald's. The question is how much do I save by not stopping at Maria's? And so this is if I go straight to McDonald's. Go straight. No stop. Okay. To get to McDonald's via Maria's house would be 16 plus 30. I've got to go to Maria's house and then to McDonald's. That gives me 46 miles. So how much distance do I save by not stopping at Maria's house? That would be 46 minus 34. It saves me 12 miles saved if I walk straight there instead of stopping. So I could say, hey, Maria, meet me there. Okay, so that's the Pythagorean theorem. Now the new part for this chapter, for this section rather, is the converse of the Pythagorean theorem, using it backwards. And what that means is if I have a right triangle, the Pythagorean theorem works. So if the Pythagorean theorem works, then I should have a right triangle. So if I can find a squared plus b squared and say, oh, it does equal c squared, that should mean I have a right triangle. Again, c is the hypotenuse. A and B are the legs. I'm going to switch them this time just to demonstrate. It doesn't matter which leg is A and which is B, as long as C is the hypotenuse. So how do we test this? Well, to test this, the first thing to identify is still the hypotenuse. And the way we identify that is by finding the biggest number. 5 is the biggest number. So that means it goes by itself, 5 squared. And then the other two numbers go together. It'll be 3 squared and 4 squared. And what we're hoping that these are equal. So 5 squared is 25, 3 squared is 9, 4 squared is 16, 25, 9 plus 16 is 25. Yes, it works. So it does make a right triangle. Let's try this one. Again, the first step is to identify the largest number. That's 13. 13 squared goes here. The other two go together, 5 squared plus 12 squared. 13 squared is 169. 5 squared is 25. 12 squared is 144. So 169 still on the left side. 144 plus 25 is 169. These are equal. That means yes, this is a right triangle. Go ahead and try these last two. So for number 3, our largest side is 14. That would make it our hypotenuse. 14 squared, 6 squared plus 11 squared. 14 squared is 196. 6 squared is 36. 11 squared is 121. 196. This is 157. These are not equal, so this is not a right triangle. And number 4, our largest side is 6. 6 squared, 4 squared plus 5 squared, 36. 16 and 25, 36. This is 41. Not equal, not a right triangle. Let's look at the next page. So from the last two examples, they weren't right triangles, then what do they make? Well, what we can tell is that if our c squared is not equal to a squared plus b squared, then it has to be either bigger or smaller. And so we have these two cases. If the hypotenuse squared is bigger, that means that the hypotenuse side of the triangle is bigger than what would make it a right triangle. So imagine this. If this was a right triangle, then C would have to be smaller, right? And so if C squared is bigger, then what we end up with is an obtuse triangle. So if the square length of the longest side of the triangle is greater than the sum of the squares of the lengths of the other two sides, then the triangle is obtuse. If C squared is bigger, the triangle angle is bigger. The angle is bigger if C squared is bigger. Which means, if the opposite of true, if C squared is smaller, then what's happening is that the length that would be needed in order to make this a right triangle would be a bigger C value. So if C is too small to be a right triangle, then this is an acute triangle. So if this is less than, then we have an acute triangle. So let's see if we can classify these. For the first one, and the steps are the same as what we just did, we want to identify the biggest number, 17 squared, and then compare that to 8 squared plus 15 squared. 17 squared is 289. 8 squared is 64. 15 is 225. 289 compared to 289. They are equal, so this is a right triangle, which is the converse of the Pythagorean theorem. We'll do one more together. So how do I know which of these is biggest? Well, if I write 4 as its square root, 4 is the square root of 16, then I can see which one is the biggest, right? So the square root of 16 is the biggest. That's the one that goes by itself. Then we have the square root of 11 squared plus the square root of 7 squared. So this is 16, 11 plus 7. 11 plus 7, careful with that, is 18. So C squared is smaller. If it's smaller, then it is acute. Go ahead and try 3 and 4. So number 3, the biggest side is 14. 14 squared, 6 squared, 11 squared. 14 squared is 196. 36 plus 121, that's 157. 196 is bigger, so that is obtuse. And then here, 6 is the biggest side. 6 squared, 4 squared, and 5 squared. 36, 16, and 25. That gives us 41. 36 is smaller than 41, so this is acute. Let's go ahead and move on to section 2. There are 2 very special cases where we can apply the Pythagorean theorem and we can come up with this pattern that it makes. And the first of those 2 cases is the 45, 45, 90 triangle. And that is an isosceles right triangle. So this is the case of an isosceles right triangle. Because we have a right angle and we have 2 congruent angles, which means 2 congruent sides. And the case of an isosceles right triangle, the 2 congruent sides, we can call them S. And then by the Pythagorean theorem, the hypotenuse would be s squared plus s squared, which is 2s squared, to give us the hypotenuse squared. And so C would be plus or minus the square root of 2s squared, which would be s times the square root of 2, choosing the positive side because it's a length. And so we come up with this pattern that anytime we have an isosceles right triangle, the hypotenuse is the leg times the square root of 2, every single time. So let's see if we can do a couple of examples. We'll do these 3 together. So to solve for x, first I recognize where my legs are and which one is my hypotenuse. And so here we have 2 times the square root of 2, which means that x equals s times the square root of 2. That makes that the side. 2 times the square root of 2 times the square root of 2. Square root of 2 times the square root of 2 is 2, so that's 2 times 2, which is 4. So all we had to do, that was a really long way of saying, I just took the side times the square root of 2. For part 2, again, here are my sides. This will be side times the square root of 2. So h equals 9 times the square root of 2. Can't simplify that, so that's it. And then here are my sides. So this is s, and this is s times the square root of 2. And so s is the same as x. 6 equals x times the square root of 2. Now this is where we can get into a little bit of trouble because we can divide by the square root of 2, no problem, but we never want to leave it in the denominator. And so we can say 6 divided by the square root of 2, we have to rationalize this. To rationalize that, it means multiplying it by the denominator as a giant 1, square root of 2 over square root of 2. Now I don't want to cancel, I don't want to simplify them out because the whole idea was to make it so that there's not a square root in the denominator anymore. So I want to multiply across 6 times the square root of 2 divided by square root of 2 times the square root of 2 is 2. So notice there's no more square root in the denominator. But then we can simplify 6 divided by 2 is 3 equals x. If you want a crash course on rationalizing functions, I would be absolutely happy to go over that during office hours. Our second case, remember I said there were 2 cases. Our second case of special use for the Pythagorean theorem is a 30, 60, 90 triangle. And really what this is this is half of an equilateral triangle. So if I take my 30, 60, 90 triangle and I draw in the other half, notice now this is an equilateral triangle. And so if this side length is s, then this is s, then the whole side for our equilateral triangle is 2s. And by the Pythagorean theorem, we can find that this height of the equilateral triangle is s times the square root of 3. And so if we're looking at it as a 30, 60, 90 triangle by itself, the hypotenuse is 2s, and the longer leg is s times the square root of 3. However, I find it most helpful to just always draw in the other half of the equilateral triangle. That way we're not mixing up which side is which. Okay, it's a lot easier, at least for me, to see that if I have the other half of my equilateral triangle, then this side is the one that was cut in half. So s and 2s, and the one on the inside of that triangle is the one with the square root of 3. So let's look at a few examples. We'll do these ones together. Okay, so here's my triangle. There's my 60-degree angle, which means that here's the other half of my equilateral triangle. That means this is my full side, this is my half side. Half of 14 is 7. The one on the inside is going to be the short side times the square root of 3. So b equals 14 over 2, which is 7. And a equals b times the square root of 3, 7 root 3. Okay, for part 2, same thing. I'm going to draw in the other half of my equilateral triangle. That makes y my half side and 12 my full side. So y equals 12 over 2, which is 6. And x on the inside of my equilateral triangle is 6 times the square root of 3. Can't be simplified. So we have y equals 6 and x equals 6 times the square root of 3. And number 3, that's my 30-degree angle. That's the one that touches the other half of my equilateral triangle, right? Because equilateral, all of the angles should be 60. So if this is 30, it needs a little bit more to make it equilateral. Okay, so then if z is 4 times the square root of 3, then what are my other sides? Well, this is the small side times the square root of 3. So z equals 4 root 3. The small side is y, so that's y root 3. If I divide by the square root of 3 on both sides, y equals 4. X is twice as long as y, so x equals 8, and y equals 4.